Welcome back. We're going to look at the last topic in this review packet, and that is electricity and magnetism. So in chemistry we looked at net negative and net positive charges being formed. To form a negative charge you gain electrons because electrons are negative. To form a positive charge you lose electrons because electrons are negative. Minus a minus, you get a positive. Electric fields are just forces that are exerted by charges, and the strength of the field depends on the size of the charge that we're talking about. Now, here's an important one. The three ways that charge can be transferred: by friction, so when we rub the rabbit skin against the PVC pipe to transfer electrons from the rabbit to the PVC and making the PVC negative. Contact or conductive transfer, touching that PVC pipe to the electroscope, which caused the electroscope leaves to pull apart from each other because they're both being charged with the same charge from that PVC rod. That negative charge flows down into both leaves, and like charges cause each other to repel. And then the third example here, and the third way of transferring charge, is the PVC attracted to the neutral soda can. That was the hanging can brought near the PVC rod, which had a negative charge, an overall negative charge. And when you brought it close to the can, all those loose electrons in a metallic bond in the can ran to the other side, because in the metal they're free to do so, making this side of the can negative, and the metal ions, the nuclei, which couldn't move, were left over here. Their electrons all ran away, or at least those valence electrons did, leaving this side of the can positive, causing the can to move towards the opposite charge of the PVC rod. So that was friction, contact or conduction, and inducting charge. Okay? When charge is flowing through something, that's what we call an electric current. That's the circuitry that we were looking at when we did the circuitry lab and the Ohm's law calculations from Canvas. And any flow of charge is an electric current. Just a quick weird note. We know that the thing that's flowing in most cases is the electron, and the electron is negative. And on the battery we have this positive terminal and the negative terminal. Whoops, let me zoom out there. Okay. So we know that charge flows from the negative and returns through a circuit to the positive side. And that's the actual flow of electrons through the circuit. And we know it's the electrons that are moving because these are the really small, agile, nimble particles that can zip through. The big, heavy ions can't really zip through a circuit. And so we don't think of them as actually moving. But when the convention was set, long, long ago, by Ben Franklin, convention was that current moves from positive to negative, from an excess to a deficiency. Think of it like a hill. You start at high and you work your way to low. That's just what we call conventional current. You don't actually need to know that word for the test. It's just what it's called, and just wanted to make sure you understood that while we know electrons are flowing in the circuit, current is actually said to flow from positive to negative in a battery through a circuit. That's not to say that positive charges can't move. In fact, inside the battery, all sorts of ions are changing positions as they're passing through membranes in the battery. So yes, positive charges can move and they can create a current. Just in a circuit, we're dealing with electrons, so it's actually backwards from whatever the circuit says. That's the real current flowing through the circuit. Alright, moving back to this. Current comes in two flavors. We only worked with one in our lab because we use batteries as our voltage source, our potential source, and batteries only provide direct current. But every time you plug something into a socket, it provides alternating current, which alternates 60 hertz, 60 cycles per second. It actually changes direction of flow 60 times every single second in America. And that's called alternating current. Moving on down. Electrical conductors allow charge to flow easily. Electrical insulators, or in circuits, we call these, if they're actually passing electrons, as resistors, will oppose the charge flow. So an insulator basically blocks the flow of charge. That's why wires are wrapped in rubber. And a resistor does not block the flow, but it impedes it. Think of it like a dam, and as water builds up behind the dam, it will spill over, but it has to build up first. It takes a certain amount of energy or potential or voltage to make things happen. That's why when you were plugging in extra light bulbs, all that extra resistance was like building the dam higher and higher, but the voltage source was not getting any stronger, so the bulbs were getting dimmer and dimmer and dimmer because the dam was impeding the current more and more and more. That's just resistance. Plastic, rubber, and air are good electric insulators. That's why the batteries don't spontaneously discharge, but when I showed you that motor, and you were looking at the copper brush and the little spindle on the motor, which were very, very close, you did notice a little spark jumping from the copper brush to the spindle. Okay? Many, many times per second, every time it was spinning past, it was sparking. And that spark is actually the plasma created by literally breaking down the air, overcoming that insulator property, and making a conductive path. Same thing lightning does. Just lightning does it on a much, much grander scale. Voltage is the word that we give to potential difference. Think of it like pressure in pipes, except it's pressure of electrons in wires. Here are two circuit diagrams. The first is in series because if we trace the path of the electrons through the circuit, they can only go this one path to return to the battery. So if I burn out one bulb, then the other bulb also burns out. Well, not burns out, but it turns off at any rate. Now in the second example, I have two paths. So the current gets here, and then like a river, it splits. It can flow down this path to get to the battery, or it can flow down this path to get to the battery. So it splits here at this junction and reunites at this junction. If this bulb burns out, then this path is broken, so it's an open circuit there, and electrons stop flowing this way, but they can still flow this way. So all the current will go through this path if this path burns out. That's why houses are wired in parallel rather than series, because you wouldn't want your burned out light bulb to shut down every electrical appliance in your house. Okay? Which answers the next several questions, in fact. So moving on to the next slide. Just matching our variables with our units, our unit possibilities. Power is measured in watts, or capital W. Current, which is an I, which I know has no obvious relationship with the word current at all, is measured in amperes, or amps for short. Voltage is measured in volts. Resistance is measured in ohms, and the shorthand symbol is the Greek letter omega. It's the thing that looks like a horseshoe. Moving on, electrical energy is measured in kilowatt hours, just by your power company, and time is measured in seconds. So just a little quick math down here. Electrical power, this formula was not one that we actually used in class. It's one that is in your reference tables, however, and you know what power is, you know what voltage is, and you know what current is. So you just have to take the 240 volts that you are given, times the 27 amp current, or ampere current, and multiply together, you get 6,480 watts, or for short, 6.48 kilowatts. All right, a power tool uses about 12 amperes of current and has a power rating of 1440 watts. What's the voltage required to run this tool? So I have the power, I have my amperage, but I don't have the voltage. So I've plugged everything into the equation. Now I'll solve for voltage by dividing by 12 on both sides. That cancels out. 1440 divided by 12 gives me 120 volts. That is the standard household voltage running through a electrical outlet or socket in the United States, except for things like ovens and dryers, which run on 240 volts. Moving down, voltage of 120 and a current of 5 amperes. What is the resistance inside this circuit? So voltage equals current times resistance, so we can rearrange to solve for R by dividing by I on both sides. V divided by I, 120 divided by 5, resistance is 24, and the units are ohms. If the battery in the circuit above is 24 volts and the resistance is 12 ohms, what is the current? So 24 divided by 12, same equation, Ohm's law, 2 amperes of current. If you use a clothes dryer for 2 hours that has a power rating of 5.4 kilowatts, what is the electrical energy usage equivalent to? Well, since it's kilowatt hours, we're multiplying kW times H, so we're multiplying 2 hours by 5.4 kilowatts and getting 10.8 kilowatt hours of electrical energy that has been used. And if you wanted to know how much that cost, for example, that would be about 10 cents roughly per kilowatt hour, so a little over $1 in electrical energy used. What is the current in a 120 volt circuit if the resistance in it is 20 ohms? Same Ohm's law equation. Voltage divided by resistance gives us amperage. 120 over 20 gives us 6. Okay? And that is the end of the review packet. There will be other videos that come up later today that go through topics that you requested that I make a short video on, and there will be some that are devoted to just sort of going through the standards. Also, you might want to check out the breakdown of the questions on the test. I did post that to Canvas, and it tells you the percentage of the test that comes from each one of those standards, those large standards, not all the little tiny bullet points. There's only a few of them on the test. All right, see you in the next video.